Hello, ladies and gentlemen, and welcome back to the 2002 Euclid contest. This is the big written scholarship paper, the 2002 contest put out by the University of Waterloo. You can get a copy of this contest by clicking the link in the description. So we're on question number 10. And it should be the hardest question on the contest. This is the last one. So this video will wrap up the 2002 Euclid. A triangle is called Heronian if each of its side lengths is an integer and its area is also an integer. A triangle is called Pythagorean if it is right-angled and each of its side lengths is an integer. So you should already be familiar with the Pythagorean triangles, but Heronian triangles, I'm guessing that it has something to do with Heron's formula. And Heron's formula, for those who don't know, is a way to compute the area of any triangle just from its side lengths. And I think that's pretty nifty. So each of the side lengths of a Heronian triangle is an integer, and its area is also an integer. That sort of invokes to me the idea of Heron's formula, which we may need. I don't know. I haven't actually seen the A, B, and C. I haven't read those out yet. But if we need it, I'll bring it up, and I'll show you a very interesting formula. So, A part, we got 3 parts to go here. Show that every Pythagorean triangle is Heronian. Okay, so Pythagorean is right angle, each of the side lengths is an integer, so it's already got the first condition of being a Heronian triangle. We just need to show that the area is also an integer. Okay, so what are we going to do here? Well, let's draw a picture of a Pythagorean triangle and talk a little bit about it. So, we have a Pythagorean triangle right-angled, and all the A, B, and C, each of these side lengths are integers. So we got a Pythagorean triangle here. Okay. So then by definition, these sides are integers, so it remains to show that the area is an integer. Okay, so we need to show that the area is an integer. What can we do for that? Well, what's the formula for the area? I noticed that I have a base of A and a height of B. So base equals A, height equals B. So the area pretty clearly is 1/2 base times height, or AB over 2. So if at least one of A or B is even, we're all done. Okay, if one of them's even, then it'll cancel out with the 2, and we'll just be left with an integer area. Okay, so we need to show that at least one of the legs of any Pythagorean triangle must be even. Okay? So I can really only think of one way to do that, and that's with modular arithmetic. Now, if you're unfamiliar with modular arithmetic, it's not that bad. It's basically just doing all of regular arithmetic, addition, subtraction, multiplication, division, but with remainders of numbers. So you work modulo a certain number, say modulo 10. Then the only numbers in existence are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All the remainders when you divide by 10. Okay? And you do all your multiplication and your subtraction and everything like that, and all the math still works out. It's really nice. But I was once shown that, actually I've seen it several times, but I was once shown that you can prove that one of the legs of a right angle triangle must always be even by, it's a proof by contradiction, and you work modulo 4. Squares have a very interesting pattern when you do modulo 4. Okay, so if you've never seen this proof before, that's okay. You can take a look here and you tuck it under your belt. So, just going to do a little claim. All squares have a remainder of 0 or 1 when divided by 4. Okay. This is true also of, I think, when you divide by 3, all squares are either 0 or 1. You'll never get a remainder of 2 for a square when you divide by 3. But we just need the divide by 4 one right now. I don't think it's true with 5. I think with 5 you can get some other ones. Just running through them mentally. Yeah, you can get 0, 1, and 4. I think are the only ones for squares when you divide by 5. Anyway, so we're going to prove this. So we're going to let k squared be any square. Either k is even or odd. If k is even, well, all even numbers have the same form. You can write k as 2t. So it's twice another number. Then k squared is just 2t squared, which is 4t squared, which has a remainder of 0 when we divide it by 4, because it's a multiple of 4. If k is odd, then we can write as k as an even number plus 1. All odd numbers look like an even number plus 1. So 2t plus 1. Then k squared is going to be 2t plus 1 squared. And that's going to be 4t squared plus 4t plus 1. Which has a remainder of 1. Because 4t squared, well, that's a multiple of 4. So that gives us a remainder of 0. 4t, another multiple of 4. And then there's just this 1 left over. So we have a remainder of 1. And that finishes off our little claim. All squares have a remainder of 0 or 1 when we divide by 4. So, and this is just something we need in order to do the proof. Okay. Suppose we had a Pythagorean triangle that had A and B odd. So if they're both odd, then A times B is odd, and we can't divide by 2 and get an integer. So this wouldn't be a Heronian triangle. So we're going to let A be 2s plus 1. We're going to let B be 2t plus 1. So they're both odd numbers. They're both odd numbers, so we can write them as even numbers plus 1. We know that c squared is a squared plus b squared. So we can plug in our new forms for a and b in here. So that's going to be 4s squared plus 4s plus 1 plus 4t squared plus 4t plus 1, which is 4 times s squared plus s plus t squared plus t plus 2. So c squared would have a remainder of 2. But that's impossible. We just took the time to show that any integer squared has a remainder of 1 or 0 when divided by 2. So our assumption that we could have both the legs be odd was wrong. It came out to gibberish. This is called a proof by contradiction. So at least one of A and B is always even. They could both be even, but they can never both be odd. And that was the last thing we needed to show. Every Pythagorean triangle is Heronian. Because A times B will always be an even number, and that means that we're always going to get A times B over 2 as an integer. And that's the area. So the area is always an integer. Okay. I didn't expect a little detour with modular arithmetic, although maybe, just maybe, that's how question 10 is shaping up. This is only part A. Maybe part B we'll have to do mod 5 or something. Or maybe in part C we'll bring it back. We'll have to work modulo 4 again to show that something can or can't happen. This is the only way that I can think of off the top of my head to show that one of the legs of a Pythagorean triangle is even. So this is the one I went for. And so this usually question part A and part B, if it's a 3 or 4 part question, usually these are planting the seeds of the ideas you're going to use in C and D. So I'm starting to think modular arithmetic. I could be wrong. Maybe there's a simpler way to do this and I just can't think of it. But this is what I'm starting to think. Working with remainders, that's what's on my mind. Okay. But as I say, that's only part A. We've got part B and part C left. It might be a good idea to read B and C together, and maybe, because C is going to be the big hard one, because it's at the very end. So knowing what C is might impact how we choose to handle B, and it probably would have chosen how we impact A as well. But let's see. So B, show that every odd integer greater than 1 is the side of some Pythagorean triangle. Okay, and C, find a Heronian triangle which has all different side lengths and no side length divisible by 3, 5, 7, or 11. So divisible by certain numbers, I'm thinking, yeah, modular arithmetic, working with remainders might be the way to go. So already I'm confident in how I handled A. And now B, show that every odd integer greater than 1 is a side length of some Pythagorean triangle. Okay. So let's just think mentally, does this even make sense? Well, let's list out some Pythagorean triangles that we know, and we should know a fair bunch if we're doing question number 10. But they're usually called Pythagorean triples. You just list out the side lengths. So some Pythagorean triples are, well, there's the famous 3, 4, 5. The next one I can usually think of is 5, 12, 13. We can always double this and get 6, 8, 10. 7, 24, and 25, that's one that I recommend people know. 8, 15, 17. And that usually does it. 9, 12, 15. Those are basically multiples of 3, 4, 5, and these ones are the ones that I recommend people know. But if I stretch my brain a little bit, I'm pretty sure I can do... I think there's another one with 9, isn't there? Yeah, 9, 40, and 41, I'm pretty sure. But I'll grab my calculator and double check. So 40 squared. 41 squared. Yep, 81. Okay. And because I've seen something like this before. I saw it at a math camp a long, long time ago. 11, I think it's 60 and 61. There's also 10, 24, 26, and I'm about tapped out on my Pythagorean triangles here. I just want to double check that 11, 60, and 61. I think that one's right as well. Yeah. So the ones of interest here, and so I'm noticing a pattern, the ones of interest here are the ones where here's 3, here's 5, 7, this one with the 9, because this one's just a multiple, and this one with the 11. I'm thinking I'm generalizing a pattern. I notice that there's a difference of 1 each time here. Okay? So what I want to do is I want to say, okay, our odd number is going to be 2k plus 1. And then how can I get the 4 from the 3? Just in terms of k. How can I get the 5? Well, the 5 should be 1 more than the 4. Okay. So we're going to generalize a pattern. And once we've got a pattern in our mind, we don't need to say, oh, where did this idea come from? We don't need to say, oh, we're generalizing a pattern. We just need to, because the question is just asking us, can we get odd numbers that do this? If you want to justify it by saying, here's my pattern, and this is what I'm noticing, that's fine. But if you just give a triple, you know, it'll start with 2k plus 1, and then you'll get a form for the next one and a form for the last one, and you prove that that's a Pythagorean triple. That's all that's required. Okay. So you don't need to have some giant intuition. You can just say, I've found a pattern, or you can even just say to yourself, I have a pattern, and I'm generalizing it to get my answer. I'm generalizing it to get a nice general form. So the triples I'm concerned with are 3, 4, 5, 5, 12, 13, 7, 24, and you'll notice that we have an even number as the other leg, because that's got to be there. 7, 24, 25, 9, 40, and 41, 11, 60, and 61. Okay, so we'll have a triple that looks like this, A, B, C. And A will look like 2k plus 1. Okay, we'll go from 1, 2, 3, yada, yada, yada. Okay. And the other thing we're noticing is C is B plus 1. So we really just need to get B. Well, is this enough? Well, we know that C squared is equal to B squared plus A squared. So C squared, that's B plus 1 squared. And then A squared is 2k plus 1 squared. We want everything in terms of k. So we'll get B squared plus 2b plus 1. Just foiling that out. B squared plus, and we'll have 4k squared plus 4k plus 1. So the b squareds are going to cancel. The 1s are going to cancel. And now we're left with b is 4k squared plus 4k all over 2, which is 2. We can take out a factor of k, and we'll get k plus 1 here. So 2k plus 1, 2k, k plus 1, and 2k, k plus 1, plus 1. Should work. They're clearly all integers. And we clearly have a squared plus b squared is equal to c squared. And that implies that we get a right angle triangle. So yeah, it works. If you wanted to, you could say, this is all my side work. This is going to be my final answer. Let's verify it. And then if we want to do it that way, we can verify a squared plus b squared is equal to c squared. You don't need to if you did it the way I did it, because we figured out what b was by assuming that this was true. But let's verify it nonetheless. Square here, 2k, k plus 1 squared, and then 2k, k plus 1 plus 1 all squared. So that's going to be 4 squared plus 4k plus 1 plus 4k squared, k plus 1 squared. I might need to expand that out. And then we'll have 4k squared, k plus 1 squared, plus 2, 2k, k plus 1, plus 1 squared, which is 1. Okay. So the 1's cancel out, those cancel out, and we're going to be left with 4k squared plus 4k is equal to, the 2 times 2 is 4k, k plus 1, which of course is 4k squared plus 4k. So it does work. We did verify. We did double check it. That's great. And we know we're going to be able to get every odd integer here, because 2k plus 1 is every odd integer. Notice, if you wanted a side length of 1, you'd have to have k is 0, but that would mean that our b has a side length of 0, and our c has a side length of 1, and that's a degenerate triangle. It's just a flat triangle, and that doesn't work. So that's why they said every odd integer greater than 1. Okay. So that's b part. Now, there was another way you could probably do it, just as a little aside. And this is only if you're sort of in the know, but every, and you know, if you haven't seen this before, this is a great thing to know. But every Pythagorean triangle can be written as, let's see, it's a times u squared minus v squared, 2auv, and a u squared plus v squared. Alright, so these are our two legs. One of them clearly even, and this is our hypotenuse here. So if you had known this form, you could have said, well, I want every odd number. Can every odd number be written as this way? Well, yeah, take a as 1, and take u and v to be consecutive integers. So, you know, to get we'd let a be 1, and we would let u be k plus 1, and v be k. So I think they should be positive integers as well, by the way. And so that would force k to be at least 1, and then we'd get the 3, we'd get 5, we'd get 7. The a is in here is just to get all the multiples, like 6, 8, 10, 9, 12, 15. It's really the u and the v that do all the work to get to Pythagorean. And this is every Pythagorean triangle. Okay? All of them, even that weird 8, 15, 17. But this is just a little aside. If you've seen something like this, they would accept this answer. Okay? And it's a nice little piece of knowledge. Every Pythagorean triple can be written this way. It's useful. Who knows? Maybe it'll be useful for C part, but I'm thinking C part we'll have to do some modular arithmetic. You could also, if you knew that every Pythagorean triple looked this way, you could probably prove that, well, no, you already know that one's even, so you wouldn't need to do an argument modulo 4. Okay, I'm crazy. Let's go on to C part. Useful to know about Pythagorean triangles. Okay, so C, once again, find a Heronian triangle which has all side lengths different and no side length divisible by 3, 5, 7, or 11. Okay. Well, all side lengths different suggests to me that there's probably some isosceles triangle out there or some equilateral triangle that is Heronian that works, but they're trying to avoid that answer for some reason. Well, to be honest, A and B had very little to do with Heronian triangles. I mean, A had the definition, B had nothing to do with them. So what we might want to do is, my guess is we've done so much with Pythagorean triangles, I'm betting Pythagorean triangles are going to be the answer. I think perhaps a Pythagorean triangle will work. So let's see if we can find a Pythagorean triangle that doesn't have 3s, 5, 7, or 11 as the factors of any of its side lengths. I think that's the way to go. I'm betting that it's going to just be some weird triangle, Pythagorean triangle, and maybe B part will help us. Okay? So, let's take a look here. So I suspect and this is based on A, because we took the time to say that Pythagorean triangles were Heronian. I could be wrong, but with such emphasis on Pythagorean triangles and very little emphasis on Heronian triangles, I'm going to guess it's got to be Pythagorean triangle. Will be a Pythagorean triangle. Because, I mean, notice that the factors that we're excluding are 3, 5, 7, and 11. They're just the first odd primes, not even. So we can have an even side length. Okay? We can have an even side length, and if we couldn't have an even side length, if they had said you can't also have a factor of 2, that would have immediately ruled out Pythagorean triangles, because remember what we proved. Every Pythagorean triangle has a side length that's divisible by 2. Could have many of them, but at least one of the legs is divisible by 2. We know that. That's a fact. So the fact that they left the 2 out makes me even more confident in this. But I still am not done. I don't have a proof, so I can't be absolutely certain that a Pythagorean triangle is going to be the answer. So we got to do a little more digging, a little more investigating. So let's look at some Pythagorean triangles. We know that every odd number will be the leg of one of the Pythagorean triangles. So what are some of the triangles that we've got? Well, let's just list out our triangles again. I'll list out the odd ones that we used last time together. And then there's also these other ones here. So 6, 8, 10, 8, 15, 17, 9, 12, 15. Another good one is 10, 24, 26. 12, 16, 20. These are all just multiples, though, except for this one here. He's pretty interesting. I really like the 8, 15, 17 triangle, because there's really nothing else like it in the first few. So we have 9, what was it, 40, 41. We have 11, 60, 61. And now I'm actually going to use our theorem, and I'm going to get us all the way up to 15 again. Because that way then I'll have 1, 2, 3 triangles that have 15s in them. And I think that's a suitable stopping place. So 13, that's 2k plus 1, so in that case k is 6. So I'll have 2 times k plus 1, and that's going to be 2 times 6 times 7. That's going to be 42 times, so that's 84. So this one's going to have to be 85. So for 15, that's 2k plus 1, and that k is 7. So we'll have 7 times 8 times 2, so that's 56 times 2. So we have 112, 113. So now we're getting into pretty big numbers here. So let's take a look. Do any of these have multiples of 3? Well, yeah, there's a multiple of 3, there's a multiple of 3, there's a multiple of 3. Multiple of 3, multiple of 3, multiple of 3. Actually, this one has a bunch of them. Multiple of 3. Multiple of 3. Multiple of 3, multiple of 3. Alright, so already we're out of luck because we seem to have multiples of 3 all over the place. How about multiples of 5? 1, 2, 3, there's a multiple of 5, there's a multiple of 5, multiple of 5. I wonder if they've played a cruel joke on us, and that there's always a multiple of 3, there's always a multiple of 5, always a multiple of 7. The 7 one I don't think is true. So maybe there is always a multiple of 5 and always a multiple of 3, in which case a Pythagorean triangle is never going to work. There's a 7. There's a 7. I don't think either of those are multiples of 7. No. That's it for the multiples of 7. How about multiples of 11? Well, there's one right off the bat. Not seeing any more multiples of 11, but there seems to always be a multiple of 3 and a multiple of 5 in Pythagorean triples. So this causes me a bit of a problem. I can't use a Pythagorean triangle, and so now I'm back stuck thinking. So we have a choice to make. Can we try and make a Heronian triangle another way? And maybe we'll have to use Heron's formula. But I think that'll be pretty hard because we'll have to choose all 3 sides at the same time. Or maybe there's some way to use a couple Pythagorean triangles together. Or maybe I just haven't gone far enough. I mean, maybe the question is you have to use that formula we worked out in Part B, but there's some weird, much larger number in the works there. So, I'd actually like to know, just as an aside, do we always get a multiple of 3 and 5? I mean, at least even if we just always get a multiple of 3 in our Pythagorean triangles, we'll know that there isn't a bigger one out there that'll work. We do have to seek some other method. So I think I'm going to use that general form that I just talked about, the A, U, and V thing, to see if I can ensure that there's always a multiple of 3 in every Pythagorean triple. Because maybe there isn't. Maybe there's some really big one with a side length of 171 and a height. Actually, no, that's a multiple of 3. 173. Something like that. Okay. So let's check. So let's check for multiples of 3. So everyone looks like this. Obviously, A can't be a multiple of 3, otherwise they're all multiples of 3. Okay, so if U or V are multiples of 3, then we're stuck. So we'll assume that U and V are not multiples of 3. Okay. So let's see here. If U is 3s plus 1 and V is 3s plus 1, and this middle one is not going to be a multiple of 3. That's great. But how about this one? U squared is going to be 9s squared plus 6s plus 1. And then V is going to be 9, oops, that should be a T. 9t squared plus 6t, so that'll be minus 6t. Minus 1, and these guys are going to cancel out, and this is a multiple of 3. Okay, so they can't both have a remainder of 1. Fine. How about U has a remainder of 1, V has a remainder of 2. I'm doing this just to ensure that all Pythagorean triangles have a multiple of 3 somewhere in there. What do we have here? We'll have a u squared, so I don't care what a is. It's really just a question of, is u squared minus v squared, is that a multiple of 3? And as I mentioned, I think before, when you square something, you either get a 0 or a 1. So I think this difference is always going to be a multiple of 3. So those guys cancel to give us minus 3, and this is a multiple of 3, because 9, 6, 9, 12, and 3. Okay, well, we got 2 more cases to go. So u is the plus 2. And v is the plus 1. So u squared minus v squared. That's going to be 9s squared plus 12s plus 4 minus 9t squared minus 16 minus 1. Again, we're going to get a multiple of 3. Okay, and the last one, and I'm pretty sure this is going to fail as well. We got u squared minus v squared is 9s squared plus 12s plus 4 minus 9t squared minus 12t minus 4. Yeah, multiple of 12. Or multiple of 4. Of 3. Multiple of 3. Good. Okay, so. So we always have a side of length 3. Okay, and I'm betting that similar analysis will probably show you can always have a side length of length 5, although it might not be one of the legs. The u squared plus v squared will probably come into play at some point. Because notice the 3, 4, 5, the 5 is in the hypotenuse there. Anyway, so that does rule out every Pythagorean triangle. We have absolutely ruled it out, but we're still not closer to a solution. Showing which triangles don't work doesn't really help us. There's an infinite number of triangles. But this is just work for us that we have indeed ruled out. We don't need to look for a bigger Pythagorean triangle. None of them will do the job. None of them will satisfy C. So I either write down Heron's formula, which I've been talking a fair bit about, and try and work with that, or I'm betting, and I bet that a Pythagorean triangle would work, so maybe this isn't the safest bet because the last one didn't work out. But I still think the amount of Pythagorean triangles we've seen here, we have got to have some way that we can use, I guess, more than one Pythagorean triangle to get a Heronian triangle. Okay? So, what would that look like? Well, we need to make a triangle up of smaller triangles. So if we can't think of a way to do that, then we're going to be pretty stuck, and we'll have to think of another method. But if you think about any triangle, if you wanted the area, you would drop the altitude to the base. Well, that turns it into 2 right-angle triangles with the same sort of side length. So if we approach it from that way, because they're Pythagorean triangles, so they'll have integer area, an integer area, and the sum of 2 integers is going to be an integer area, so there's no harm with that. We'll have an integer side, an integer side, and 2 integers gets us another integer side length. But I hear you saying, well, you just figured out that one of the side lengths always has a multiple of 3. One of them always seems to have a multiple of 5, probably. What can we do about this? Well, we have 2 triangles here, but they're stitched together. And so maybe if we picked the right side length, the right 2 triangles, we can make it so this side length sort of eats everything. Okay? So my instinct is actually just to use the same triangle twice, but they said we can't have the same side length, so we can't have an isosceles triangle, so this isn't allowed. So we'll have to come up with 2 different Pythagorean triples that have a common length. And we want that common length to be at least a multiple of 3 and multiple of 5, possibly even a multiple of 2, or 7, or 11, all the nasty stuff we've seen so far. So, well, let's get cracking. What are our Pythagorean triples again? 3, 4, 5. Actually, if I want the multiple of 3 and the 5 there, I have to start thinking 15s again, because I want a 3 and a 5. So I should be looking for multiples of 15, multiples of 30, that sort of stuff. I think there was one with 60. Yeah, I think 11, 60, and 61 worked just fine. So if I could get another one that has a 60 in there, we'd be all set. The next one's too big. And these ones here are too small. We want one that has everyone that... Actually, let's just go back and look at it. Because we actually did all the work and said which ones have multiples of 3 and which ones have multiples of 5 and everything. So yeah, this 60 right here, with its 11, I'm a little hesitant of. But the 60, the 84, they seem to be the way to go. And over on our non-generated ones, 8, 15, and 17. The 15 seemed to be the only offender, and 15 and 60, if I multiplied this triangle here by 4, kept this one, and added them up the right way, I think the 11 would disappear with 4 times 8, which is 32, so that would be 43 as a side. We'd have 61 as a side, and 4 times 17, which is 68 as a side, and none of those have 3, 5, 7, or 11. I think that's it. I think that'll work just fine. So we already did enough of the work. I don't even need to list all these out. So we're going to take 11, 60, and 61. So we do need 2 Pythagorean triangles here. And not 8, 15, 17. But we're going to multiply it by 4 to get 32, 60, and 68. And then we'll have 68, we'll have 32, we'll have 11, we'll have 61, and we'll have our 60 buried in here, and this will be 43. So we have a triangle with integer sides. And 3, 5, 7, and 11, none of them divide 43, that's a prime. None of them divide 61, that's a prime. And none of them divide 68, that's 2 2s and a 17. And 17 is neatly out of the range of these primes. And since Pythagorean triangles have integer area by A, this triangle has integer plus integer has integer area 2. So this is a Heronian triangle. And it's got the conditions that we want. And so that finishes off the question. Right, that's all we were asked for in C part. Find a Heronian triangle, all different side lengths, got that. No side length divisible by 3, 5, 7, or 11, got that. And it is Heronian because each of the side lengths are integers, and its area is the sum of 2 integers, which is therefore an integer. Okay, so we had a little detour there. We thought maybe a Pythagorean triangle would work. It didn't, but it taught us a valuable lesson. We took a look at our Pythagorean triangles, and that actually saved us some time at the end. We looked at our Pythagorean triangles, saw where they failed. There were 3s, there were 5s. We actually did a little side job and proved that there's always going to be a 3, so that we should stop looking at Pythagorean triangles. But then it was a choice of work with a brand new formula, which I still never wrote down, but I will in some video. So be on the lookout for that, or use Pythagorean triangles. And we went with more Pythagorean triangles because the question was so Pythagorean triangle heavy. They're not trying to trick you with these things. They try and plant the seeds in earlier parts for the big question at the end. That's good question design. Gets you thinking along the right lines, but you still need to know certain things, like your Pythagorean triples, like that 8, 15, 17. That wasn't going to be generated by our formula in B part. But if you didn't know the 11, 60, 61, that would have been generated by the formula in B part. So you had to have a little bit of knowledge and use your part B. So I think overall, a very nice question. It was pretty good. And yeah, that's it. That's it for question number 10, and that's it for the 2002 Euclid. I threw some knowledge about Pythagorean triangles and modular arithmetic out there at you. So if you didn't know any of that, great learning experience there. And the next Euclid will be the 2003, which is the first year the Euclid actually became the big paper. In 2002, they also had a Descartes for grade 13. So next year, the Euclid is the big scholarship paper. This year was just sort of the warm-up to the Descartes. And I think the next contest I'm about to go do is the grade 7 Gauss from 2003. So if you're interested in either of them, I'm sure by the time you're watching this, those are up. Unless you happen to catch this right when I uploaded it, in which case, thank you for probably being a subscriber. Okay, so I have ranted and rambled at the end of this question for far too long, taking up way too much time. I'll see you guys in the next video. Thank you for watching, and that was the 2002 Euclid.